Let's calc gang, look at some mechanics and materials. So let's solve this problem. So I just solved 3.27, which is the problem before this, and it has pretty much the same setup. So we're given a specimen that has a diameter and length that's given to us, and then it's also given us Poisson's ratio. So then we're given this graph, and are told if a load of 60 kilonewtons is applied, we need to find the new diameter and the new length, right? It's going to stretch out, so its length is going to increase, its diameter is going to decrease. Actually, I think it's going to decrease, and you know what I mean. So let's solve it, right? So really quick, Poisson's ratio is the change, or it's the strain, excuse me, in the lateral direction, which is basically the diameter, over the strain in the long direction, which is the length. So really quick, I already solved for E in the last problem. I didn't think I needed to do it again. So the modulus of elasticity, right? It's equal to the slope of this elastic region. So it's a linear line, so you can really easily find the slope taking 490 dividing it by 0.07, and you get that it's equal to 70 gigapascals. So now let's move on to the rest of the question and start solving. So let's start with the long direction. How about that? So if we want to find the change in diameter of the long direction, we're going to need to use the equation stress is equal to the modulus of elasticity times strain. So let's expand everything to get what we need. So let's start with this, right? Stress is equal to force over area. Force over area is equal to the modulus of elasticity. And then strain long is going to be length final minus length original over length original. Right? L prime is the new length, and that's what we want to solve for. So let's rearrange this stuff to get it in the position we want. So let's divide by E. E over AE. AE. And then let's multiply that L to get on top. And then let's add the L. And this is going to be equal to L prime. So check the algebra if you want on this, but that's how you get there. So let's plug in our numbers. So the force is 60 kilonewtons. So we use 60. The length of the specimen is 15.8 millimeters, so we're going to have to convert that to meters. All right, 1, 2, 3, that's right. Area, it's going to be pi over 4. Diameter squared, 12.7 squared. And then the modulus of elasticity, 70. So there we go. We can go ahead and solve for that. This is going to be L prime. Make sure I did it right, of course. 60, oh, I forgot to add the L to it. Right, don't forget to add the original length. So we're taking that and we're adding it to the original length. Let's just do 0.0508 is equal to L prime, right? That's what we're solving for. So you do this, and you get that it's equal to 0.05111437 meters. And that's our first answer right there. So we can see that it increased a little bit. It went from 50.8 to 51.1. So now we need to use Poisson's ratio, right? We're given Poisson's ratio, and from that we can find the strain laterally. So basically for that we need to find the strain in the long direction. We could have solved it earlier, but let's just solve it here now. So strain long, right, is equal to L prime minus L over L. We know these numbers, right? We just found L prime, so it's 0.05111437 minus L original, which is 0.058. I'm drawing off the board here, but 0.058. You get that E long, or epsilon long, strain in the long direction, is 0.006766 millimeters per millimeter. That's a useful number. Let's go back to Poisson's ratio. So we know Poisson ratio is 0.35. So let's take E long and multiply it over to the other side to get E long. Poisson's ratio is equal to E lat, and don't forget that negative sign. So let's plug in what we know. So E long we found over there, negative 0.006766. Poisson's ratio 0.35 is equal to E lat. And you solve for that, and you get it's negative 0.002368. How do they draw that? Millimeters per millimeter. It's a good number right there. So now we need to solve for the change in diameter. So now we can use the equation. Strain lat is equal to the change in diameter over the original diameter, d prime minus d over d. So we know d prime is what we're solving for. So we want to move this equation around. So let's multiply by d and then add that d. So we get d epsilon lat plus d is equal to d prime. So let's put in those numbers, right? Diameter original, 12.7. E lat, 0.00 negative, don't forget the negative, 0.2368. We have to add that to the original, 12.7, right? Then we're gonna get that d prime is equal to, you do the math, looking at the wrong thing here, but this is gonna be 12.67 millimeters. Yep. There you go, so that's your final answer. So you can see that the diameter decreased in length, but the length increased from here. So yeah, pretty cool question. Not too tricky, just about knowing Poisson's ratio and all these equations that we've learned up to this point in the class. So if you have any questions, if you're struggling, feel free to check out my playlist. I have a whole lot of practice problems on there. Ask me questions in the comments, and I'll see you in the next video. Peace.